The cryptography we've looked at and studied so far has been symmetric. That means that the sender and receiver share a key, and they use the same key for encryption and for decryption, and the adversary is assumed to not know that key. Something exciting in the 1970s relative to essentially millennia of cryptography was the possibility of asymmetric or public key encryption, which meant that the encryption key and decryption key were different, and the encryption key could be made public and even known to the adversary. So we're now going to abord that whole area, and the starting point will be a study of number theory from a perspective a little different from a math class, in that we are going to be interested not just in the math but in the computational aspects. So number theory is I think, a fun topic, very concrete. Often we'll see that the example we'll look at is just the numbers 1 through 10, fingers on our hands, and come up with all kinds of properties and ways of looking at them that you don't normally think about. But nonetheless, it's perhaps useful, despite the intrinsic interest of the subject, to start with this motivating example, which is the core primitive of public key crypto, and that's called secret key exchange. So the problem here is that Alice and Bob have never met in person. They only communicate over the internet, and they want to send messages to each other in such a way that at the end they have a shared key and the adversary does not know that key. So the protocol, you can imagine, is supposed to work something like this. So Alice will perform some operations. She's allowed to pick things at random. As a function of whatever she picks, she will compute something which becomes a message sent to Bob. This little x is a random choice. The big X is what's sent over here. Bob likewise will pick stuff at random, perform some computations, and then compute something to send to Alice. And then each of them will apply some public functions to their original choices, Alice's choice being this one here, and to the information Bob sent, in her case, to get a key. Likewise, Bob will compute a certain public function on his original random choices and the information Alice sent and get a key. And what we want at the end of the protocol is that the keys are equal. Alice and Bob get the same key. Now, by itself, of course, that's trivial. They could just decide their key is 0. But it should also be the case that the adversary, who is allowed to eavesdrop on the conversation and sees the public parts, can't figure out what this key is. The adversary doesn't know what little x is, but it knows big X. It doesn't know little y, but it knows big Y. And that information is not sufficient to get it the key. Now, to be clear, this is not a specific protocol. This is a template. I'm just asking, is there some way for us to fill in these dotted lines to instantiate these f sub a and f sub b functions so that this actually works and we have a solution to this problem? And that problem is what's called secret key exchange. So this, you could try to do this. Maybe if you first look at it, it seems a plausible thing. We know how to do encryption, authentication, so many things. How could you approach it? If you try to approach it with the tools we studied so far, however, you find you run into a little bit of a trouble. So all of these tools, which are fundamentally of a style that's existed for a very long time, don't seem to have any way to yield a solution for secret key exchange. Furthermore, until the 70s, when it was done, many people thought that this was actually impossible. You can give it a try. How would you create a protocol as we just described? Maybe you could have Alice pick a key and encrypt something and send that to Bob. But under what would you encrypt? To encrypt something that Bob can decrypt, they already need to have a shared key and you don't have one. And it's a kind of difficult to get out of that situation. So in the mid-70s, Diffie and Hellman proposed a candidate protocol for secret key exchange, and that was the birth of asymmetric or public key crypto, which since then has been wildly influential, and it's something you now use every day. So TLS takes advantage of this setting. Before we uh, continue with the number theory, perhaps it would be worthwhile, and in particular as an introduction to it, to have a look at this video, which shows us kind of informal description of the protocol and how you might
Imagine two people who have never met could do an amazing trick. Alice and Bob are allowed to communicate over a line which is tapped, so any message they pass will be intercepted by Eve, who is always listening. The trick is to agree on a secret numerical key without Eve also obtaining a copy. How is this possible? First, let's explore how this trick is done using colors. So, how could Alice and Bob agree on a secret color without Eve finding it out? The trick is based on two facts. One, it's easy to mix two colors together to make a third color. And two, given a mixed color, it's hard to reverse it in order to find the exact original colors. This is the basis for a lock, easy in one direction, hard in the reverse direction. This is known as a one-way function. Now, the solution works as follows. First, they publicly agree on a starting color, say yellow. Next, Alice and Bob both randomly select private colors and mix them into the public yellow in order to disguise their private color. Now, Alice keeps her private color and sends her mixture to Bob, and Bob keeps his private color and sends his mixture to Alice. Now the heart of the trick. Alice and Bob add their private colors to the other person's mixture and arrive at a shared secret color. Notice how Eve is unable to determine this color since she needs one of the private colors to do so. And that is the trick. Now, to do this with numbers, we need a numerical procedure which is easy in one direction and hard in the reverse direction. This brings us to modular arithmetic, which is known as clock arithmetic. For example, to find 42 mod 12, we take a rope of length 46 units and wrap it around a clock of 12 units, which is called the modulus, and wherever the rope ends is the solution. So we say 42 mod 12 is congruent to 10. Easy. Now, to make this work, we need a prime modulus, such as 17 instead of 12. Then we find the primitive root of 17, which is a number that has no factors in common, in this case 3. And it has this important property that when raised to different exponents, the solution distributes uniformly around the clock. 3 is known as the generator. So if we raise 3 to any exponent x, the solution is equally likely to be any integer between 0 and 17. Now, the reverse procedure is hard. Say, given 12, find the exponent 3 needs to be raised to. This is called the discrete logarithm problem. And now we have our one-way function. Easy to perform, but hard to reverse. Given 12, you would have to resort to trial and error in order to find the matching exponent. How hard is this? Well, with small numbers, it's easy. But if we use a prime modulus which is hundreds of digits long, it starts to get seriously hard. Even if you had access to all the computational power on Earth, it could take thousands of years or more to find the answer. So the strength of a one-way function is based on the time needed to reverse it. Now this is our solution. First, Alice and Bob publicly agree on a prime modulus and a generator, for example 17 and 3. Then Alice selects a private random number, say 54, and calculates 3 to the power 54 mod 17 and sends this result publicly to Bob. Then Bob selects his private random number, say 24, and calculates 3 to the power 24 mod 17, and sends this result publicly to Alice. And now the heart of the trick. Alice takes Bob's public result and raises it to the power of her private number, which gives 3 to the power 24 times 54, and she obtains the shared secret, which in this case is 1. Bob takes Alice's public result and raises it to the power of his private number, which gives 3 to the power 54 times 24, resulting in the same shared secret. Notice they did the same calculation with the exponents in a different order. 24 times 54 is the same as 54 times 24. Without one of the private numbers, Eve will not be able to find the solution. And this is how it's done. While Eve is stuck grinding away at the discrete logarithm problem, and with large enough numbers, this will literally take forever.
Okay, so what that showed you is that this key exchange problem can be solved with kind of physical means using colors. And then it showed you a mathematical solution. And it's the second that we'll be pursuing and looking into. And this summarizes it. And even though at this point we don't have a lot of number theory under our belt, it's still possible, as the video showed, to actually give a pretty complete description of how the protocol works. And you can actually see how it's done. So the setup is that Alice and Bob are assumed to know a large prime number p that's, let's say, created and placed in a standard or made public in some way, and another number g, which is called a generator. We will later see what these generators are. They're also called primitive elements as per the video. Now let zp minus 1 be the set of all numbers between 0 and p minus 2. What Alice does is she picks a random number from this set, and then she raises g to that power, except that she doesn't do that just as an integer, but having done it, takes the result mod p, and that value big X is sent over to Bob. Bob will perform similar steps. He'll pick a random number y from this set zp minus 1. He'll raise g to the power y and take the result modulo p. And that results big Y is sent over to Alice over here. Now Alice takes the thing that Bob sent and raises it to the power little x. Bob correspondingly takes the thing that Alice sent and raises it to the power little y. And the magic of the math or algebra is that these two values are equal. It's not that hard to see. If you look at the number g to the power, the product of little x and little y, you can write it this way. And in that case, it looks like big Y to the little x, which is what Alice computes. You can write it this way, and then it looks like big X to little y, which is what Bob computes. So they have got the same key. But it also turns out that for appropriately chosen parameters, we don't seem to have any known way for an eavesdropper given big X and big Y to figure out that key due to the hardness of the discrete log problem, as was discussed in the video. Now, that description leaves a lot of things ununderstood or unaddressed. Some of those include these. How do we get these large primes? If I tell you to get some prime, it's easy enough. 5 is a prime. But we want primes that are hundreds to thousands of bits long. And how do you even find them? How large is large enough? Why are we asking it to be large? What does it mean for G to be a generator modulo P? What's the definition of that? Once we have a definition, how do we find G's that have that property? How do Alice and Bob compute the operations they need in the protocol? Alice is supposed to raise G to the power X and get the result mod p. But both g and p will be very, very big numbers. How do they design algorithms and software that do this in reasonable amounts of time? Why is the security property true? Why is it that the adversary, given the exchange flows, has a tough time computing the key? So it's stuff like this that we're going to answer with our little foray into number theory. Now, the math in this, I think, in number theory is fairly simple, and it begins in particular in a fairly dry kind of way. But the definitions slowly accumulate to the point where they become quite powerful. And if you feel like you're seeing a lot of math, it's actually, one might reflect, a bit surprising that this little math is enough to solve such a difficult problem, that the secret key exchange in the end doesn't rely on math more difficult than in an undergrad algebra course in the math department. Okay, so with that introduction, let's get going. So we'll start with just a bunch of basic notation. So by z, we mean the set of integers, both positive and negative. By n, the set of natural numbers, which is all non-negative integers. And the strictly positive integers will be denoted z plus. The greatest common divisor function takes two integers a and n and returns the largest number d that divides both of them. For example, if I run GCD with inputs 30 and 70, I'm asking what divides both 30 and 70, and of those, what is the largest such number? And that would be 10. The arguments a and n to the GCD function could be negative, but the resulting GCD is always positive. When we work in cryptography, we want to stay within some finite set. There'll be some finite set of objects that play the roles of messages, ciphertexts, and other kinds of things. And this introduces the main such sets. So first we fix a number n, a positive integer. We often call it a modulus. Associated to that are a bunch of sets. The first is well known, z mod n, or z sub n, is just all numbers between 0 and n minus 1. But the interpretation that we can now give to it, given somehow the hint of the use of modular arithmetic we've already seen, is that these are all possible remainders you can get on dividing things by n. Effectively, we will be working with numbers, but we will be really only interested in remainders modulo something. Now, if you take all the numbers in Zn, there's a certain subset of them called Z star n that's also of interest. And that's formed by picking out all of those that have no non-trivial divisor with n. So A belongs to Zn star if A belongs to Zn, and the greatest common divisor of A and n is just 1. All numbers which have some divisor other than 1 that also divides n are eliminated. Now, it's clear that the size of the set Zn is n. There are n things in it. But what's the size of Zn star? How many such things are there? That may not be readily apparent, and it comes up often enough that mathematicians have a special notation and name for it. It's called the phi function, or the Euler phi or totient function, phi of n, and it returns the size of the set Zn star. As an example, suppose n was 12. It's very easy to see what Z12 is, all numbers between 0 and 11. But what is Z star 12? You look at the above list and throw away anything that has a common divisor with 12. So for example, you throw away 0. Why? Because 12 divides 0 and 12 divides 12. You keep 1. You then throw away 2 because 2 divides 12. You have to throw away 3 and 4 as well, but you keep 5, and so on. So what's left here are 1, 5, 7, and 11, And now if we are asked what is phi of 12, it's just the size of the above set, so that'll return 4. There's a whole bunch of different operations on numbers that we're going to need. These will be performed by encryption routines, and in fact, software you have on your computer that's used for various secure transactions implements stuff like this. And we will start by simply visiting operations that you've known since middle school. But there's going to be a bit of a difference as we get into them, which is that we're also going to care about how long it takes uh, for an algorithm to perform this. So integer division is the name given to the function that takes two inputs, integers a and n, and divides a by n, and it returns both the quotient and the remainder. So mathematically what that means is a can be written as quotient times n plus remainder, where the definition of remainder is that it's a number which is non-negative but strictly smaller than the thing you're dividing by. So now if you want to compute a mod n, well, it's by definition just the remainder. So integer division in particular gives you an algorithm for the mod function. So for example, if you run integer division on 17 and 3, it'll divide 17 by 3 to get a quotient of 5 and a remainder of 2. Often we have numbers which may be large, but really the only thing we're interested in is their remainders modulo some other number n. So we use this notation to say A is equivalent to B mod n if when you compute A mod n and B mod n, you get back the same thing. So for example, 17 and 4 are equivalent mod 3 because 17 mod 3 is what, 2, and 14 mod 3 is also 2. There's an abstraction that's very well known in algebra called a group. And it's useful for us in cryptography to have this abstraction because we can then leverage a lot of general facts about groups called group theory and somehow see things in a more unified way. If you've taken algebra courses in the math department, you already know something like this. But for self-containment here, I'm going to recall the definitions of groups. Our treatment will be very uh, fast compared to a math treatment in the sense that we won't necessarily prove a lot of things, but just kind of describe them by example. So a group has two components. The first is a set. So there's some set of points. It could be Zn, for example, or even the set of all integers. And the second is a binary operation on that set. What does this mean? It just means that if I hand you 2 points in the set, this operation returns some third value. It just computes something based on them. The word binary refers to the fact that there are 2 inputs, that's all. Okay, so examples. Let's look at the set of integers mod 12 relatively prime to 12. We saw that on a prior slide. And let's say multiplication modulo 12 is our operation. So a dot b is ab mod 12. Now we tend to use this dot notation to kind of connote multiplication, but in general it's an entirely abstract operation. You can define it to be a whole bunch of things, anything you might want. And that must be kept in mind when interpreting things. So now when you have a set like the above and some kind of operation has been defined, we say that this set is a group under that operation if it satisfies certain properties, and there are 4 of them, and they're called closure, associativity, identity, and inverse. The fact that we'll have coming out of this, and which we will use a lot, is that certain sets are examples of groups under certain operations, and specifically integers mod n relatively prime to n, Zn star, is a group when the operation is defined as multiplication modulo n. So take 2 integers in the set Zn star, form the integer product, but then what you return is the remainder of that when you divide by n. And we'll see why that's a group and later why that's useful. So let's look at these properties. So closure simply says that when you apply this operation to 2 points, the result is also inside the same group. It's in the same set in which you started. So often with groups and their properties, it's easier to understand non-examples or counterexamples than examples. So for example, consider a set Z12. So that's all numbers between 0 and 11. And let's define an operation on it. A times B equals AB. What is AB here? Just integer product, right? So 7 times 5 returns 35. That's a perfectly fine binary operation, but it doesn't satisfy closure. Why is that? Because 35 is not in Z12. Of course, it's very easy to fix that. What we can do is just, instead of returning the product AB, we return the product modulo 12. In that case, it's quite easy to see that you do have closure. A more interesting example is the integers mod n relatively prime to n. So say n is some positive integer, and we look at Zn star as the set G. And let's define the operation on A and B to be A times B, integer product, but then you return the result modulo n. And we claim it satisfies closure. Now, an interesting element of that is that you might think at first, well, of course, because A times B mod n is smaller than n, and so that tells you that you have closure. But there's actually an interesting mathematical element here. You need the result AB mod n to be in G, and G is the n star. That means that that result must be relatively prime to n. The GCD of A times B mod n and n must be 1, otherwise it's not in Zn star. So we are saying then that underlying this is a mathematical claim. If these 2 points A and B are in here, meaning their GCDs with n are 1, then when you take the product mod n, the GCD of that with n continues to be 1. So as an example, if n was 12, then we have the set Z star 12, and we saw earlier that that set is just these 4 points. Closure is telling us that if I take 2 points in here, any 2, 5 and 7, and take them take their product mod 12, what will I get? Well, 7 times 5, 35, and 35 mod 12, how do I compute that? Well, let's see, 12 times 2 is 24, 24 plus 11 is 35, so 11. And what closure is saying is, look, 11 is actually here. If I take 2 things in here and multiply them mod 12, I will never get back an answer of, say, 2 or 4 or 6. And closure is telling you that. Now, this property actually needs a proof. If you go to a math class, they'll prove it for you. Not that it's hard, but it's a bit extraneous for us. So we'll take that as a fact. But if you like math, you can go ahead and prove the fact. Okay. The second property of a group is what's called associativity. Now, associativity is something that you probably have encountered all along, all the way from when you first started looking at numbers, but you may not necessarily have named it or seen it abstractly. All it says is that suppose I want to operate on 3 things, A, B, and C. If I could first operate on A and B, get a result, and then operate on C. Alternatively, I could first operate on B and C, get a result, and then operate on A and that result. In other words, I could put parentheses in 2 different places. Well, associativity simply says it wouldn't matter whether you do that or not. So where you put the parentheses doesn't change the outcome. Again, we can see what happens if you're looking at Zn star. We claim that the associative property is true under multiplication mod n. And what that means translated is that if you take first A times B mod n, and then multiply by C and then do another mod n, It's the same as if you first multiplied b by c, took the remainder of that mod n, and then multiplied by a. Again, if you're in a math course, you could prove that in general. We won't do it, but you can see some examples. So if my numbers are 5, 7, and 11, and here I'm working, let's say in Z12, Z star 12, well, if I start here, 7 times 5 is 35, 35 mod 12 is 11. And so I get 11 times 11, and modulo 12, 121 mod 12 is 1. But I could do it another way. I could do first 7 times 11 and get 77. 77 mod 12 turns out to be 5 because 72 is a multiple of 12. Then I have 5 times 5, which is 25, and 25 mod 12 is 1. So you see that the intermediate values in the computations were very different, but the result is the same. As indicated before, it's perhaps more revealing to give examples where the property fails. That gives you a better sense of why it's a non-trivial claim. So as an exercise, try to do that. As some hints, think about subtraction, think about division, various things. Try to come up with a property where closure is true but associativity fails. The third property is that there exists a neutral or identity element. So the group must have inside it some point, and by notationally simply we'll denote it 1. And the property it has is that if I operate with a and 1, I will get back a. And that does independently of the order, whether I do a operated 1 or 1 operated a. Now, looking at something like this, one of the possible sources of confusion is to think that nothing is happening here, that this is just trivial. Of course, a times 1 is a and 1 times a is a. But remember that this 1 is not the integer 1. It's an abstract point in the group. Sometimes it is the integer 1, but it doesn't have to be. This operation is not necessarily integer multiplication. It could be something very different, although for us it's usually integer multiplication modulo something. So the claim is quite abstract and hence could be a non-trivial. Continuing our example, we claim that for any positive integer n, the set of points modulo n and relatively prime to n, z, n star, with the operation a times b mod n, does have an identity element, and moreover that identity element is in fact the integer 1. Why is that? Because now it's pretty clear a times 1 really is a, that's just integer multiplication, and modulo n doesn't change anything, and same with 1 times a. So quite easy to see that 1 really is the identity element over here. The final group property is less trivial. It says that you have the possibility of division. That's not captured by talking explicitly about division, but rather by talking about inverses of points in the group. Now, inverses are effectively how we do division. For example, if I tell you to divide something by 5, what you're really doing is multiplying that something by 1 over 5. So what enables division is the fact that there's something called 1 over 5. So this is going to abstract that out. What it says is that the inverse property is true in a group G if anytime you hand me some point in the group, I can find another point B which is kind of 1 over A. And what does it mean to be 1 over A? It means operating on A and B, or B and A, the order doesn't matter, gets you back what? 1, but 1 is the identity element of the group in general. So given that B then is kind of 1 over A, we introduce notation of this form. We write A to the power negative 1, and what it denotes is simply this B over here. So again, something to be wary about is that this is just notation. A is an abstract object, and A inverse simply says go find the point in the group B which has the property that A times B is 1, and that's what this has as value. So again, let's look at our running example. If n is a positive integer and the group is Zn star, and we've defined A.B to be integer product mod n, then what inverses is saying is if I take any point in Zn star, there exists another point such that the product mod n is 1, is the identity element. And that's not necessarily obvious. It's not clear why such a point should exist. You can try it out. So let's say n was 12 as usual, and let a be 5. So what is the inverse of 5? I have to look at this equation. 5 times b mod 12 is 1. And then I have to solve it for b. That's what the answer is. So, well, we don't have too many methods for solving at the moment. The best we can do is just try. We know that the answer is something in the group, and the group is Z star 12, which has only 4 points in it, 1, 5, 7, and 11. Well, let's just try them. Could B be 1? No, 5 times 1 is 5, not 12. Could B be 5? 5 times 5 is 25, and 25 mod 12 is 1. So we conclude that B is actually 5. And later we'll see better ways of performing the computation. But here some of the things to be careful about is note that when we ask you for 5 inverse, you don't do something like say, it's 1 over 5 and start writing fractions. There are no fractions here. The inverse is going to be an integer. It has to be a member of this set. And so it turns out that for some reason, 5 is its own inverse in this set. So playing with these might be useful toward understanding groups better. A very simple example of a group is Zn. We've been playing with Zn star. Zn is the case where you have all the numbers 0 through n minus 1. And there you set the operation to addition. So the dot means I take the sum of a and b as integers and then reduce mod n. You don't always have to work with numbers. You can work with strings. Take the set of strings of some length and let the operation be XOR of the two strings. You can show that that's a group. Again, it's nice to have non-examples. Go back to strings and take the operation to be bitwise AND. Prove it's not a group. Numbers are fun to play with. One of the things that we'll see as we go along is that we can find ways to perform computations which a priori would look very daunting due to the sizes of the numbers involved. So as a simple starting point, suppose you were asked to compute the product of these 4 integers and then take the result mod 21. Well, naively, how would you do this? Well, you would multiply all of them, and that could take a little bit. Maybe you'd need a calculator, but 8 times 5 is 40, times 10 is 400, then you have to do 400 times 16, and it turns out the result is 6400. And then finally you would compute that mod 21. So that means you have to divide 6400 by 21 and find the remainder. And that does look like a pain. Maybe you'd Google or get up a calculator or whatever. It turns out the remainder is 16. However, here's a quick way, and this way I claim you don't need any calculator. It's simply the observation that due to associativity and the group properties, you can perform your mods as you go along on the fly. So when you've computed 5 times 8 and got 40, you don't stay with the 40, you immediately reduce mod 21. And so what is 40 mod 21? It's quite easy to see that it's 19. And now you take 19 forward. So 19 times 10 is 190. Again, you don't go on, but you first reduce mod 21. So this one, you need a little bit more work, but you see that 9 times 21 is 189. So 189 is a multiple of 21, and so 190 divided by 21 will use a remainder of 1. And then it's easy taking the 1 forward and multiplying by 16 mod 21, you get 16. So you can use these things freely as you go along, and you'll see that it makes things quite a bit easier. There are various operations that we'll need algorithmically. When we see how encryption is done, it will be working on numbers in one of these groups, in particular Zn star, and we will be raising things to powers. You saw that in the Diffie-Hellman key exchange, where Alice had a G and she raised it to the power x modulo p. That is simply saying let the group be Zp star and raise G to the power x inside that group. So to be able to think about and work with stuff like that, we introduce exponentiation. So let G be a group and let A be a point in it. Then raising A to the 0th power, we define the result to be the identity element of the group. Again, you're probably used to the fact that if A is a number, A to the power 0 is the integer 1. That's a special case of this, but this is more general. And the aspect that is helpful towards understanding it is that this A to the 0 equal 1 is not a fact, it's a definition. Of course, once you define it, it becomes a fact. But before having defined it, A to the power 0 didn't really have a meaning, and now we give it a meaning. For positive n, similarly, A with the superscript of n doesn't yet have a meaning. Again, thinking ahead, we know that if A is an integer and n is another integer, we kind of know what we'd like to say. But we define this in the group to be operate on A n times. There's more going on here than it seems. These are group operations. Closure says the result is in the group. Associativity allows me to not put any parentheses anywhere because it wouldn't matter. And so this definition as written makes sense. We also want to define what it means to raise A to negative powers, and we define it this way. This equation, again, the difficulty with understanding it is exactly that it looks like some kind of trivial tautology, but it isn't. What it's saying is, remember that A has an inverse in the group, and we denote it this way. So I define this notation to be take that inverse and multiply it by itself n times to get another group element. Okay, having made all these definitions, what you can see as a result is that all the usual properties that we like to have with numbers are kind of replicated in this abstract group. So for any positive or negative integers, the raising of A to the power I or j is now well defined. So let's look at these identities, and in looking at them, it's worthwhile to disambiguate object types. Note that A here is a group element. It's an abstract quantity as far as we're concerned. But I and j are just normal integers, 3 and 5 and negative 10 and whatever. Okay, raising A to the I plus j, it says returns A to the I dot A to the j. Again, you could say, well, of course, that's how things work. But this is an abstract statement in a group, and the reason it works like that is to go back to these definitions and see that they imply this property. Similarly, raising A to the power of product is the same as taking A to the power I, getting a group element out and raising that group element to the j, or raising A to the power j, getting a possibly different group element out and raising that to the power I. A to the negative I, defined like this, is also A to the power I inverse. This is again not a tautology, because what it's saying is that the result of A inverse multiplied by itself I times is the same as if I first looked at multiplying A by itself I times, took the group inverse of that and returned that. So those two things are the same. Now, once you have all these, what it actually tells you is you can start playing with exponents and manipulating things just as you're used to. And so all the usual stuff happens, but now we know that that stuff is well justified. You can also see, for example, remember that in the Diffie-Hellman key exchange, the key was g to the power of the product of x and y. So a would be g, x would be I, and y would be j. And this equation is exactly what tells you that the two different ways for Alice and Bob to compute it result in the same key. So let's try to do some exponentiation. Let's say n was 14. So we're looking at the integers mod 14 relatively prime to 14. And what happens when you raise 5 to the power 3? Well, in that group, what you're saying is that you compute 5 times 5 times 5, and then you take the result modulo n. So the integer result is 25 times 5, but we're going to reduce that mod 14. We could multiply 25 by 5, I guess we get 125 and then reduce that. But we could also use some of our tricks. Our tricks tell us that we can reduce the 25 right away. 25 mod 14 is 11. And then continue. And then we get 11 times 5 is 55. And 55 mod 14 is 1. It's been written with these equivalent signs. These mean that these numbers are equal modulo 14. What about 5 to the negative 3? Again, the question is being asked inside this group over here, so it's all mod 14, even though the 14 doesn't appear explicitly there. So 5 to the negative 3 will be take the inverse of 5 and multiply by it by itself 3 times. So we'd have to know what the inverse of 5 is. What does that mean? We have to find a number such that 5 times b is 1 mod 14. Again, there's not much to do besides search, and after a little bit of trial and error, we see that 3 works. 5 times 3 is 15, and 15 is 1 mod 14. So it's 3 multiplied by itself 3 times, and that's 27. And then you have to do 27 mod 14, and that turns out to be 13. We're often interested in the size of the set that comprises the group. Often enough that mathematicians like to give this a special name. They call it the group order. So the order of the group simply returns its size. Remember, bars around a set returns its size. So for example, we might say, what is the order of z star 21? We know that this is a group by our general facts, but how many points are in it? So that's not so easy to figure out because this set is somewhat complicated. It's all numbers between 0 and 20 that have no common divisor with 21. But we can take a brute force approach. We just figure out what the set is. How do we do that? We take all numbers from 1 through 20 and we throw away anything that has a common divisor with 21. So 1 is okay, 2 is okay, 3 is not okay because 3 divides 21, 4 is okay, 5 fine, 6 is not okay because 3 divides 6 and 3 divides 21, and so forth. And finally we count it up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we get that the order of this group is 12. There's a bunch of very general facts in group theory that we'll appeal to over and over again. And one of the most basic is this one over here. So suppose we have any group. Well, it has some order. Let's say the group is finite, so this order is some integer m. For example, g could be z star 21, in which case m is 12. Now take a point a inside the group. We know what it means to raise a to powers. We've defined that. A particular choice of that power is this group order. M is just some integer. I could raise a to the power m inside the group. Multiply a by itself m times, see what happens. Well, the fact says that you will get back the identity element. This is true no matter what point in the group you start with. Any point you start with, you'll get back the identity element. We're not going to prove this. It's a kind of fun proof, but you can do it in the first few weeks of an algebra class. But we could look at this example. So with this being our group, what it tells us is that take some point in there, for example 5, and raise it to the power of the group order, which is 12. Well, let's see what happens. While doing this, I'll also try to play around with little tricks that make the computation easy. A priori, raising 5 to the 12th power is a bit annoying in terms of work. But what if I write it as 5 to the power 3 and then 4? Splitting up 12 as 3 times 4. Well, 5 cubed modulo what? To be careful, modulo 21 here is what? So 5 times 5 is 21, and 5 times 5 is 25, mod 21 is 4, and 4 times 5 is 20. So I get 20, and now raised to the power 4. Another little trick, 20 mod 21 is the same as negative 1. It's fine to have negative numbers here, and very easy to compute negative 1 to the power 4 is just 1. If you didn't follow the number theory computation tricks, fine. Just look at the conclusion. 5 to the 12 mod 21 is 1. And that just verifies this. So try another number, 8, raise it to the 12th power, go through the computations, you'll get back 1. And what the fact is saying, anything in this list raised to the 12th power is 1. A few things may be worth remembering in these computations as you go forward. Remember that the computations are done mod 21. 21 is the base because the operation of the group is multiplication mod 21. The 12 is the exponent over here. So we'll use that if a command. Here's a slight extension or corollary that's also useful. Again, let G be a group. It has some order, we'll call that M, and let A be any point in the group. I want to raise A to some power I. Here I is any integer, positive or negative, and think of it as rather big. What the corollary says is that all that matters is the result of dividing I by the group order M. You may as well raise A to that power. It's the same as raising A to the power I. This operation I mod M is performed in the exponent. These numbers I and M are just normal integers, and you can take that result. But A to the power something is of course a group element, and since here we haven't named any specific group, it's a purely abstract operation. But this is saying that in all groups you have this fact. So this time I'm going to give a proof, and the reason is just that the proof is quite revealing and it's one line long. So we are given this number I, and we're given the group order M. Let's divide I by M using our integer division function, and that'll give us back a quotient and remainder. That means we can write I as M cubed plus R. Now this is just in our heads in some sense. It's a mathematical operation we're doing for the proof. We also know that R is of course I mod M. That's what the remainder is defined to be. Now let's raise A to the power I. Since I is M cubed plus R, that looks like this. But we can write that as A to the power M to the power Q times A to the power R by the properties of exponentiation. But A to the power M by our first fact is the identity. If you take the identity and raise it to the qth power, it'll remain the identity. So all this is just 1 and goes away, and we are left with A to the power R. So quite simple to see that this is true. So let's exercise that by again seeing how you could perform relatively complex looking computations quite simply. So suppose I asked you, compute 5 to the power 74 mod 21. So raise 5 to the 74th power and give me the remainder on division by 21. If you knew nothing of number theory and group theory, you might think of this as pretty daunting. Without a calculator, it's going to be pretty hard, and it might even overflow some very primitive calculators. But my claim is that with what we know, it's actually something you can do by hand quite easily. So how would we do that? We would first identify that this is something happening in a group, and that group is Z star 21. Once we know that, we say, how would we pattern match with the corollary? Well, A would be 5 and I would be 74. So we're raising A to the power I in Z star 21 as the group. What then would be the value of n? It would be the order of z star 21. That may be a bit of a pain to compute, but luckily on the prior slide we computed it, and we know that it's 12. So the corollary tells us that rather than trying to directly raise 5 to the 74, I can first reduce 74 mod 12 and raise 5 only to that. Reducing 74 mod 12 is pretty easy. 72 is a multiple of 12, so 74 mod 12 is 2. So we only have to raise 5 to the power 2 mod 21, and 5 squared is 25, mod 21 is 4. Okay. So application of that corollary made this really quite easy to do by hand. You can try a few of these. These are similar exercises which ask you to compute either inverses in a group, or do exponentiations in a group, or compute the size of Zn star for some value of n, and so forth. Now, in the math description or class, you can stop with just the mathematical description of a group and all the nice properties and go on to many nice mathematical results about them. But we want to develop algorithms based on this, and eventually encryption will be using all of these operations implemented in our software or hardware. So we want to talk about algorithms on numbers. And for algorithms to be implemented in our encryption software, they better be relatively efficient. So we are now going to think about what that means. When you take an algorithms course, you've learned that efficiency is a function of some kind of length of the input. So, for example, when you have a graph algorithm like binary search or like depth first search or something, it might have some running time. We would express this running time as order n or order n squared or whatever. Similarly, we want to talk about algorithms on numbers, and we want to know what n is. And the answer is n is the bit length of the number. You don't always see this in normal algorithms classes because you just don't deal with big numbers. You have 32-bit or 64-bit numbers. But crypto numbers are ginormous. So they reach magnitudes like 2 to the power 512 to 2 to the power thousands. You can still store them relatively efficiently in computer memory. It's just hundreds to thousands of bits of memory. But then algorithms have to operate on those binary representations. And it's as a function of that length of the number that we then measure algorithmic running time. We might overload this bar notation and apply it also to a number. And it's supposed to return the number of bits in the binary encoding. So for example, applying this to 7 doesn't return the absolute value, but it returns 3 because 7 in binary is 111, and there are 3 digits in there. So this is a summary of various algorithms that we will routinely be using in public key cryptography. And the purpose of giving it as a table is so you can go back to this table when you need to do operations and numbers and see, is there something here that's going to help me that I can use? And you will also know from this what is its running time. We start with very simple things, integer addition and multiplication. There's no mod here, these are just standard operations. And we see something about their running time. For example, addition is a linear operation. Its running time is the sum of the lengths of the two numbers. Again, this returns the binary length. Multiplication is quadratic. Integer division is quadratic. There's mod, and then there's operation extended GCD, which we'll talk about. We haven't defined it yet. And then there are operations to perform, algorithms to perform various group operations like inverses. And there's a way to perform exponentiation, either modulo something or in a general group. So some of those facts are simply go back to how you did things in middle school or elementary school or whatever, and just observe that you had an algorithm and then you can now see what its running time was. So for example, addition, you know how to do addition. You write down your two numbers and column by column you add them. And you can see that now with your algorithmic expertise, that will take time linear in the lengths of the numbers. So that explains the more trivial examples, and we'll jump ahead to something more interesting, which is the extended GCD. And the reason it's interesting is that it's used in a somewhat non-obvious way in this area. So we know what the GCD is. If I give you two numbers a and n, the GCD is the largest common divisor. What the extended GCD does is that it returns the GCD as one of its outputs, but it has two other outputs, and those two are weights, and they're chosen to satisfy this equation, that the GCD can be written as the first number times the first weight plus the second number times the second weight. Of course, you may ask why on earth we would want these weights. That'll emerge in a little bit. But just to check we know what these mean, if I asked you for the extended GCD of 12 and 20, you would first say, okay, what is the GCD itself? And you would come up with 4, because 4 divides 12, 4 divides 20, and nothing larger than 4 divides both 12 and 20. Now our task is write 4 as 12 times something plus 20 times something. You have to play around a little bit, but one choice is if I put -3 here, I get 12 times that is -36. And if I put a 2 here, plus 40, which is 4. If you're trying to find these things, by the way, you'll quickly realize you have to use negative numbers. They're not only allowed, but necessary as weights. Otherwise, when you have positive numbers here, it's not going to work out. Okay, so we know what the extended GCD is, and next we're going to say we want an algorithm for it, and how do we get one? So the way this algorithm is devised is to go back to Euclid's classical method for computing the GCD and enhance it to keep track of these weights so that you get the extended GCD. It's easier seen as a recursive procedure. So suppose I want the GCD of a and n. I start by dividing a by n to get a quotient and remainder. This lemma tells us that the GCD of a and n is the same as the GCD of the second number n and the remainder over here. We won't prove that lemma. Why is it useful? Because the numbers here are smaller than the ones here. Usually n is smaller than a and r is smaller than n. So by this operation, we're slowly reducing down, and when we get to very small numbers, then it's quite easy to compute the GCD just by looking at them. So here's the recursive algorithm corresponding to that. I want to compute the GCD of a and n, which is any pair of numbers which are not both 0. The base case of the recursion is that n is 0. If n is 0, what is the GCD of a and n? Well, the largest thing dividing both a and n will then just be a. And the weights are simple because a can be written as 1 times a plus 0 times n. If n is non-zero, we start using the lemma. We divide a by n, get a quotient and remainder, and run the algorithm recursively on n and r, as indicated here. The lemma tells us that our GCD will be correct. We next have to think about how do we get the weights. Well, we had the weights over here, and recursion can tell us that here we will get correct weights to write d as a linear combination of n and r. Then you can play around a bit with the math. I won't go through the details, but you can update these weights in such a way that they become weights for a and n. And those we call a prime and n prime, and we return them. So modulo some details, let's say you believe that works. Then another question is, what is the running time? This turns out not to be such an easy analysis, but eventually it can be shown that the running time is quadratic, meaning you take the lengths of a and n and multiply them, and that's the running time. So we remember that the extended GCD can be computed in that much time. Now, another fact that we'll sometimes need is that not only is the running time small, but the numbers coming out of it are not too big. The weights have a size that's linear in the size of the original numbers. They're not too much larger than the original numbers, and that's sometimes useful. This mention of Fibonacci numbers is because they arise in the analysis of the running time. It's kind of an interesting use of those numbers. One of the reasons that extended GCD is important is that it allows us to compute modular inverses. So say that we have Zn star, the group Zn star. We know that for any n, Zn star is a group, and we have a point A in the group. By the group property, it has an inverse. So there is a point B such that A times B is 1 modulo n. But now I don't want to just know that, I want to compute it. We've done some examples in the past, and the way we computed inverses is just by brute search. We would try a few possibilities, just exhaustively working our way through the group until we found an inverse. That doesn't work very well for the sizes of groups that we'll be seeing in actual cryptography usage. So let's ask ourselves, if I want, given A and Zn star, meaning GCD of A and n is 1, to compute the inverse that I know mathematically exists, I have to solve the equation A times A prime is 1 mod n for A prime. The trick is run extended GCD on A and n, and you get back this triple dA prime and n prime. Looking at that, you may say, wait, why do I even ask what the GCD is? Because I already know the GCD is 1. I'm starting with that assumption. So D will be 1. What's valuable is the weights. They tell us that 1 is a linear combination of A and n, A times A prime plus n times n prime. However, if I take this equation mod n, this part just goes away because n mod n is 0. What I'm left with is that 1 is A times A prime mod n, and that's exactly what this equation wants. So in summary, how do I compute modular inverses? I run extended GCD on A and n, and then I return A prime. For good measure, I take it mod n if necessary. And all this shows that it's a good inverse. So this is quite a nice thing. We now have the ability to compute modular inverses in quadratic time. So even on very, very large groups, we will actually have fast algorithms for inverses. Encryption is going to be done through exponentiation. Exponentiation emerges as the most central operation and also the most costly one. People spend a lot of time optimizing it. We saw it in the Diffie-Hellman key exchange. Raising g to the power x was exponentiation, and so forth. Mathematically, we know what it is. Our question now is, I want an algorithm. I give you a group element A and an integer n, and I want to know what is a to the power n. Well, this looks like an awfully simple algorithm to design. I can just start by setting y to 1 and just multiply y by itself a times. That's what the for loop does, and that's the answer. Okay, are we done? Is this a good algorithm? And this is something that comes up a lot in working with numbers, so it's worth getting used to, is that it's certainly a good algorithm in terms of the answer. It does compute the result correctly, but from the perspective of what we want, it's very, very slow. It's what we would call exponential time. Why is that? Because the running time is measured as a function of the bit length of the things involved. So thinking of n as being relatively large, of size about the order of the group, and we want to measure the running time as a function of the size of the binary representative of the group numbers, then we see that that would be the log of n, and so when we have an algorithm whose running time is order n, it's order 2 to the power the binary length of n. So in terms of the binary length of n, it's actually exponential. And that's the problem here. And furthermore, this is not some just kind of theoretical quibble. For example, if n is around 2 to the power 512, which is what happens for our encryption algorithms, this will take 2 to the power 512 steps, which is completely ridiculous. You're not getting any sort of efficiency out of that. So what we want is a better exponentiation algorithm, and so we want some more clever algorithmic ideas. So let's see how that works. It's fairly easy to see once we look at the problem that if we keep multiplying a by itself to get it to high power, we're just doing a lot of wasted work. So here's something faster. Say I want to compute a to the power 32. I start by squaring a to get a squared. Then rather than trying to get a cubed, I square it again to get a to the fourth. And notice that that operation has the same cost as one group operation. It's just the group element a squared multiplied by itself. So kind of unit cost as far as group operations go. Then I can do it again, and I square that and I get a to the power 8, again in one group operation. And then next time a to the power 16 and a to the power 32, and it only took 5 steps. Generalizing this, it's not hard to see that you can compute a to the power n in about log n steps. The caveat is that for the way we wrote it, this is only true if n is a power of 2. So if n has the form 2 to the I, then we get a to the power n in I steps. And this is exactly what we want, because I is the binary length of n, and hence this is a linear time in the number of group operations algorithm. The final time will depend on the time of the group operations, but abstractly. So what we're left with then is, well, what do we do if n is not a power of 2? It's not as simple as it looks. Suppose I want to compute a to the power 20. How might I do that? I might think, okay, I'll use this fast method, get to a to the 16, and then just multiply a to the 17, 18, 19, 20. The problem is that that part already is exponential time. It's extremely costly. The reason is that the spaces between these things are increasing exponentially. So there's a huge amount of stuff in between here, and we can't go through that exhaustively. So the method that's used is called square and multiply. And what it does is it says if we look at the binary expansion of the exponent and work with that, we can arrive directly through this squaring at the right answer. So suppose, for example, that the binary length of the exponent is 5. The exponent here is a variable. I'm just saying that its length in bits is 5. So write it in bits as b4 through b0, with b4 the most significant bit. As an integer, it says n has this binary expansion, okay, which worked out in more detail looks like this. Okay, so what we want is to compute a to the power n inside the group. So let's do it like this. Start by setting a variable y5 to the group identity element. In every step, square what you had before, and then multiply by a raised to the power the current bit in the binary expansion. So here I would square this and get a 1, and then raise a to the power b4, and that'll be a to the power b4. Next time I do it, I square what I had before, so I get this squared, which is a to the twice b4, multiplied by a to the b3, and that becomes this. And now hopefully you see what's happening. When I square this, I get a to the power 4b4 plus 2b3, and I bring in the a to the power b2. So at the end, here I have the binary expansion of n, and so I'm done. Here's the actual code, pseudocode for that type of algorithm, where we define bin of n to return the binary, to be the binary representation of n, so that it returns the bits such that n can be written in this way shown over here. When I want to raise a to the power n, the subscript here indicates that this algorithm is for the group G, and hence we'll use group operations as primitive operations. A is a member of the group, n is simply an integer. For simplicity, non-negative, but it's easy enough to adapt this to negative because we can use the inverse group operation first. Expand the exponent, get its binary representation, and then as before we do our y's through a loop. We start with the most significant bit and go down. At every step you square what you had before, multiply by a, the same a as here, to the power the current bit in the binary expansion. And unraveling what we had before, this is going to work. How do we measure its running time? Well, the loop takes what time, and this is the main gain and trick. It takes k iterations, and k is the number of bits in the binary representation of n. So that, remember, is the bars around n returns exactly k. And so now we have a linear time algorithm, which is fast. Remember, linear is in terms of group operations. So it counts this as one step. But if you then look at a specific group, you have to factor in that these group operations themselves take time. So for example, if you're in Zn star, we'll then denote the algorithm as mod exp. That will take a, n, and also the modulus big N, and it'll return a to the power n mod big N. And its running time will be this times the cost of one group operation, and that's the length of the modulus squared. And so you get this as the total running time. Now, sometimes there's confusion about stuff like this arising from the fact that we write this with an abstract group and then start instantiating it. So where is big N in this algorithm? The big N is hidden inside this. The operation here is multiply mod big N. So when you change G to a specific group Zn star, that enters, and that gives rise to this thing over here. So this exercise is illustrative of how in practice people really want to optimize exponentiation, and they consider this problem. Suppose I want to compute a to the power x times b to the power y for given ax, by, and modulo n. The obvious way is raise a to the power x, raise b to the y, take the product, mod n. There's actually a better algorithm, and this is important enough that people implement this algorithm in practice. And this effectively asks you to work out that better algorithm. So our summary then is just that at this point, hopefully all these algorithms make sense. And you can refer to this chart and keep pulling out whichever ones you want. Right? We now know what extended GCD is, or how mod inverse is done, how mod exp is done, and this was the generic exponentiation algorithm. We didn't give details of how you do all of them, for example, this one. So this is just a fact to be accepted.